Good morning, everyone. It's about time, and I'll get started. This is Zifei from dmx. Today, I'm here with my colleague Tristan, and we're excited to introduce dmx-compressor, which is a user-friendly model compression toolkit focused on the fake quantization of large language models and built on top of Torch.Fx. This toolkit simplifies the process of post-training quantization and quantization-aware training, making them more accessible to the users. So quantization plays a key role and grow exponentially in size, some now exceeding 1 trillion parameters. Quantization is crucial to run these models efficiently on specialized hardware, for example, the D-matrix hardware. Torch.Fx is a popular framework for model quantization. It allows users to produce a quantized graph module by symbolically tracing the original model and inserting quantization operations or replacing the existing operations with their quantized versions. However, using FX for quantizing LLMs presents several challenges. First, the quantized model produced by FX is a fx.GraphModule, which is no longer a first-class citizen of the PyTorch ecosystem. For example, if a user obtains a LLM from Hugging Face, it will contain specific functionalities like the generate method. However, the Torch.Fx graph module loses access to all the model attributes and methods, making it incapable of tasks such as text generation. And secondly, FX only supports static graphs, while the computation graph of LLMs are highly dynamic. Consider a llama, for example. The pipeline callable triggers the generate method of the llama model, which iteratively calls the forward function. By analyzing the input arguments to the forward function, we see that the input differs between the first and the second forward call. And if we dive into the llama model's forward function code, we see that some input arguments are conditional, controlling which blocks of code to execute. For example, if passkey values is not none, additional code is triggered for handling KV cache, resulting in a different computation graph. To address these issues, we use a double graph representation behind the scene. The process begins with an instance of a model, which can be a Hugging Face pre-trained model or a standard Torch module. We then specify tracing rules to instruct the FX tracer on which submodules to not trace through and preserve as module operations. After obtaining a FX graph module from tracing, we want to substitute the original operation nodes with new nodes that contains quantization. And we define substitution rules to map the original operations to their corresponding DMX modules, which are modules wrapped in quantization ops. So once tracing and transformation is complete, we get a graph module containing DMX modules, which is then attached to the original model and packed into a DMX model. So this double graph representation is key to maintaining the original structure of the model while ensuring that the forward function triggers the forward function of the graph module, which encompasses all the quantization operations. If we take a look into one of the DMX modules, a DMX linear, for example, we see that it preserves all the features of linear while adding quantization operations. And for memory efficiency, the parameters of the DMX modules are tied to the original modules. Okay, after that, we want to configure the quantization ops to the right format. Users can define custom format subclassing from the format class, which can be super powerful for research. Alternatively, users can also select from predefined formats, which includes the emerging microscaling formats. And next, quantization configuration rules are defined to specify which format to be applied on which operation, down to the granularity of a specific operation, and leading to a fully quantized DMX model. Now, if we take a look into the DMX linear again, we see that the input format and the weight format has been correctly configured. And to tackle the issue of FX only supporting static graphs, our solution is just-in-time tracing, which defers model tracing and transformation to runtime so that the graph can be generated based on the actual input argument. If subsequent forward calls detect changes in input that would result in a different graph, the retracing will be triggered automatically. And it is important to note that the quantization configuration is decoupled from the graph module itself, meaning that even when retracing occurs and a new graph module is generated, the existing quantization config can be seamlessly applied. And in addition, we also support the backward functionality for fine-tuning with straight-through estimators used for the quantization operations. Let's dive deeper into the process. First, we create a DMX model. At this point, no graph module exists yet. The DMX model closely resembles the original model, except that the forward function is refactored to handle JIT tracing. And next, we specify the DMX quantization configuration rules. So when input is passed in, since no graph module exists yet, tracing and transformation will be triggered, and the DMX configuration rules applied, and the input tensor will be passed through the forward function of the graph module. For subsequent inputs, the forward function will inspect whether the input will result in a graph change. If no changes are detected, it will be directly passed to the graph module. However, if the input signature changes significantly, retracing and transformation will be triggered with the configuration rules applied, and the output will be generated using the updated graph module. So now let's summarize the flow of dmx-compressor with a concrete example. Imagine a custom net model with a linear layer and two optional input arguments to the forward function. If old x is not none, it is added to x. And if use JALU is true, JALU is used as the activation function instead of ReLU. So we can see that the computation graph of this model is dependent on the input arguments, making it impossible to decide a static graph upfront. When the dmx-compressor API is invoked, it starts with a custom net instance. Wrapping this instance into a DMX model initially does not trigger tracing or transformation, and the quantization configuration rules are registered to the model by calling the configure method. When the forward function is called, the input is inspected, triggering tracing and producing a graph module. To make things clearer, we provide a tool to visualize the graph module. While the text might be small, we've enlarged it on the right. For subsequent forward passes, if the input does not necessitate any changes, the same graph module will be reused. However, changes in input, such as passing use JALU equals to true or passing old x as a tensor, will trigger retracing. As shown, the second DMX module is changed to a JALU. And an extra DMX module is created to handle the addition of x and old x. So throughout this process, we can see that the DMX modules are consistently configured according to the configuration rules that we defined earlier. The key features of dmx-compressor includes high customizability, supporting custom data formats, operations, and quantization configs. The DMX model is also highly compatible with the original model's interface so that it can be easily integrated into Hugging Face pipelines, fine-tuning processes, and more. In addition, we provide an API for the users to do other optimizations, such as quantization calibration, post-training quantization, and quantization-aware training. If you're interested in dmx-compressor, please visit our GitHub repo. For any questions or feedback, feel free to reach out or open a GitHub issue. And community contributions are also greatly welcome. Thank you. Next, I will hand over to my colleague Tristan to take one or two questions.
Thank you, Zifei. Are there any questions? Could you repeat it a little? There's a mic up here.
Hey, so does dmx support MXFP microscaling formats natively in the hardware, or is it like a compression technique and then the software-based implementation?
The base numerical format of our hardware is very similar to like the microscaling int8 format. We call it BFP16. It stands for block floating point with 8 bits of mantissa and an 8-bit shared exponent. And the tile size is like a 64 by 64 in hardware.
Okay, in one of the quantization examples, it was showing MXFP4 also. So do you support MXFP4 as well, or is it just MXInt8?
We support lower, in the Corsair version, we support lower MXInt precisions, like int4. So
okay.
Yeah.
Thank you.
Yeah. I think we have time for 2 more.
Yeah, so I have a question with regards to the JIT tracer. How does it handle graph breaks? And does it, like, if not, does it assume the whole graph needs to be traced? I guess I'm thinking of the cases that Dynamo would handle.
Right.
Yeah.
So under the hood, it's using the old FX symbolic tracing, which of course doesn't handle graph breaks. So that's a current limitation if there's something that can't be traced. However, we're sort of inspecting for graph changes, so it's an enhancement based on that. But yeah, that limitation is still there.
Got it. Thank you.
Yeah. So in the context of dmx-compressor, it's primarily a tool for researchers for fake quantization in order to get results. So from that standpoint, we think it's more principled to think about the graph not mapped to different devices. So I mean, we can sort of handle device attributes, but yeah, at least in the context of what we look at, we look at a single device. Thank you.
We probably will be hanging around at the D-Matrix booth on the other side, so if you guys want to reach out, please come and find us. Thank you.